We talked about section 8.3 and I asked you guys to work on the homework 41 through 50. Let's start today with questions from, that problem set or the previous. Jacob. 41? Sure. All right, so for 41, we're given that the vector u is -3, 8, and the vector v is 7, 2. Oh, my projector. Meh. All right, so we're given that u is the vector 3, 8, and v is the vector 7, 2. And we're asked to calculate the projection of u onto v. So to do that, we're going to use our formula. So the formula for a projection is the dot product of u and v divided by the magnitude of v squared times the vector v. So the dot product of u and v is the product of the x's plus the product of the y's. The magnitude of v is the square root of 7 squared plus 4 squared, but because that is also being squared, I'm just going to drop the squared or the square root on it. And then our vector v is just 7, 2. So -21 plus 16 is -5. 49 plus 4 is 53. And so now we just do our scalar multiplication, which gives me -35 over 53, and then -10 over 53. Does that make sense, Jacob? Cool. Luke? Sure. I'm going to copy and paste, I think, that in so I don't have to spend a half an hour or feel like writing all that information down. All right, so it says a crate weighing 80 pounds is being pulled up a ramp at an angle of elevation of 29 degrees with a force of 130 pounds. The ramp has an angle of elevation of 22 degrees. What is the amount of force being directed up the ramp? So when you read this question, how many vectors do you hear? There's 3. So there are 3 vectors. So there's the vector due to gravity interacting with the crate. There's the vector pulling the crate up the ramp. And there's a vector for the ramp itself. So let's write down the magnitudes and directions for these vectors. Now notice that there's no indication of how long the ramp is, which means that I can choose the ramp to just be a unit vector. Everybody's cool with the magnitudes and directions that I was able to pull from the story problem? I think that part should be pretty easy still. So let's talk about what's going on here then. So there's kind of two ways to approach this. Since both gravity and the pull vectors are being applied to the crate, one way we could do this is we could project both of them onto the vector r separately, calculate the magnitudes of those projections, and then think about whether we should be adding or subtracting them. So in a physics sense, if you set a crate on a ramp, what do you expect the crate to be doing? Sliding down, right? Now, if you take a crate and you put it on a ramp and you pull it up, you'd expect it to be going up. So in that sense, if we did it the way I just described, we'd want to subtract the magnitudes of those two projections. Everybody's okay with that? That the gravity magnitude projection would be subtracted from the pull projection? That's not the way that I would want to do things. Now, in this case, it's pretty obvious, like one of the forces is going to cause the crate to go down the ramp and the other was going to cause the crate to go up the ramp. But in general, that may not be really obvious. So I would prefer to take my forces that are acting on the crate, add them together, and then project that resultant vector onto the ramp. That's the way that I would choose to do this. Because if I do it that way, I don't have to think about at all whether these forces are like net moving the crate up or down the ramp. The numbers will just kind of take care of themselves and I don't really have to worry about it. So that's what I'm going to do. I'll start by turning everything into component form so that I can do my vector addition and then do my projection. Luke, so far so good with that? Okay. Okay, so what do we got here? 0, negative 80. So I got to do this one. 130 cosine 29. And then 130 sine 29. So 113.70 and then 63.03. 113.70. And the last one, so cosine 22, sine, try cosine 22, Mr. Kulik, not 2. Woo! That could have been a disaster. So I have 0.93 and 0.37. Cool how I've done that. Okay. We'll add those two vectors that are interacting at the crate. And then we're going to calculate the magnitude of the projection of those two vectors onto the ramp. To do that, though, we have a shortcut. Since we're projecting onto a unit vector, that magnitude is just going to be the dot product, or the absolute value of the dot product. Oh, well, that's pretty good. So the product of the x's plus the product of the y's. I didn't do that subtraction on my calculator, so I guess I'm going to have to use a quantity there or whatever. And I get 9906. Oops, I guess pounds up the ramp. Luke, does that feel okay? Yeah. You would do 49 similarly. They're basically the same problem with different numbers. So the trick there is just if you have more than one vector interacting with the object that's being moved up or down the ramp, just add all the vectors together and then do the projection and let the numbers take care of themselves. It's usually pretty straightforward as to what's happening. Worth pointing out to you that I didn't take the absolute value here, I guess, since the number was positive. If this was had come out to be a negative number, that would have implied it was actually sliding down the ramp, that the pull wasn't enough to like counteract gravity. So taking the absolute value here might have gotten a little bit dicey because you might have missed that because it was actually would be like down the ramp then, whatever the number is. Or if you wrote it as negative up the ramp, I guess that's a weird way of writing it, but I think it conveys the same meaning. But it didn't happen in this case, and I don't think it would happen like in a problem that I would give you, but like there's nothing to say that couldn't happen. You know what I mean? So that one's all done. And again, when it was all finally decoded and you saw how to do it, it's like, oh, not that different. Recognizing there's three vectors was the key there. Yeah. Yeah. So that was the trick. Who else? Josie? 43. So here we have that the vector v is 7, 2, and w is 5, -9. And we want to do the projection of v onto w. So just use our projection formula. So the dot product of v and w divided by the magnitude of w squared times w. So my dot product is the product of the x's plus the product of the y's. W squared is 25 plus 81, or the magnitude of w squared. And then just times w. So what do we have here? 35 minus 18. So that is 17 over 106. So 5 times 17 is 85 over 106. And then -9 times 17 is 81 plus 63, so 154 over 106. Oh my goodness, that's not right. It's 90 plus 63, so 153 over 106. That's better. And that's it. Okie doke. Who's next? Jake? 36. Says to find the angle between vectors v and w, where v is the vector -4, 5, and w is the vector -2i plus 3j. So I noticed that vector w is in that linear combination form. So the first thing I'm going to do is rewrite vector w in component form, since all my vector operation definitions were given in component form. So that's really easy. Just the coefficient on the I becomes the x component, and the coefficient on the j becomes the y component. So I'll go to my angle between two vectors formula, which is the dot product of the two vectors. Well, I get the cosine inverse of the dot product of the two vectors divided by the product of the magnitudes. So here we have cosine inverse. -4 times -2 plus 5 times 3 divided by 16 plus 5 is 41. And 4 plus 9 is 13. And then it's just calculator time. So cosine inverse, I'm going to use the fraction command so I don't have to muck around with like a million parentheses here. It's not literally a million parentheses, but I don't really have to worry about the parentheses if I use that fraction command. When I do that, I get 4.96. Alpha and then y equals, and you pick the first option from the menu that opens. I think you can also find it in the math menu somewhere. But I like that shortcut because you don't have to go mucking around through the menu. Josie? Sure. All right. Paul is sledding downhill with a 20-degree angle of incline. If Paul and the sled weigh 180 pounds, what's the force sliding down the hill?
I think this is the wrong problem.
Okay.
It's like the one where it's like the creative negligible weight is being behind an angle of 30.
I see. Yep, I just grabbed 46. My apologies. Okay. So this first sentence where it says a creative negligible weight, all that tells you is that there's no gravity vector, which is good. That's one less vector. Pulled up at an angle of elevation of 38 degrees. so there's my pull vector with a force of 120 pounds. My ramp has angle of elevation of 25, so there's my ramp vector. So just two vectors. So the magnitude of the pull is 120. The direction of the pull is 38. The ramp, we're not told how long it is, so we're going to assume it's a unit vector. And the direction of the ramp is 25. Cool. So what we're looking for is the projection of P onto R, or the magnitude of the projection of P onto R. And since R is a unit vector, I know I can do that by just taking the dot product. So that's going to be 120 cosine 38 times cosine 25 plus 120 sine 38 times sine 25. All I've done there is I just skipped writing out the vectors P and R in component form. I just went and used the magnitude. It was right there for me. You're okay, Jose?
Yeah.
Okay. And then just calculator time. That's it. So 116.92. Sure. Okay, last call here before we move on. Alrighty, that's okay. As you get further into your problem set, you run into more stuff and you want to circle back to things, that's okay. We can always do that in the future. Today we're going to do section 8.4, which is about two-dimensional vectors in space. Sounds like a cartoon to me. So, we're going to start our discussion of two-dimensional vectors in space by introducing to you yet another vector representation. Yuck, Mr. Kulik, are you serious? I'm serious, guys. So this is called IB component form in our textbook. Back when I had my, when I did this stuff, we'd call this a column vector. So the vector in component form AB just turns into the column vector AB. We call it a column vector back in the day because it looks like a column. I'll probably end up calling these things column vectors accidentally all the time, so I apologize in advance. It's just like, you had 10 years of calling them that, and then you have like 2 years of trying to change the name of it to a less descriptive name. Doesn't really work real well. But again, very easy to switch back and forth, right? There's really nothing to this. We okay? Okay. What we're going to spend most of today doing is talking about or working with vector equations for a line. So let's just say, for example, we have just some normal everyday slope-intercept equation like y equals 1/2 x plus 1. Now I know that I can represent this equation with both a equation, like I've drawn here, and a graph, right? The graph of this is going to be what? It's going to have a positive slope, not too steep, and a y-intercept around 1. We can ascertain all of that just by looking at the equation and sketching a picture, right? So one thing I can do with an equation of a line like this is I can pick a value for x, plug that in and generate a value for y, which will tell me the points that lie on this line, right? Everybody's okay with that? In a vector sense, rather than having a point 2, 2, we're going to want to talk about a point vector 2, 2. So we'd be talking about something like that. Everybody's okay there? Yes, Luke? So a point gets parentheses. A column vector also gets parentheses. No wedges. The wedges are only for regular component form, not IB component form. But that's a good question, certainly if you can't tell from my writing, which definitely at times it's probably hard to tell. Very fair to ask. Notation is important. Okay. In addition, equations for lines are also sometimes classified by slopes, right? For the equation y equals 1/2 x plus 1, what's the slope? One-half. Okay. And how do we calculate slope? Well, I mean like in general. What's that? Rise over run, or we could also describe that as change in y over change in x, right? So instead of slope in vector land, we're going to talk about a direction vector. And now, if I look at my slope, what part of my slope of 1/2 is the x part? 2. So that should be the first component in my direction vector. And which part of the slope of 1/2 is the y part? The 1. Everybody's okay there? So what we're going to be doing then is if I take some point vector and I add to that my direction vector, the resultant vector will be some new point vector, right? Now, for this to be a vector equation of a line, the vector equation that I'm about to write has to be able to generate every point vector or every point on this line. So I'm going to need something a little bit more than just the point vector and the direction vector. What I'm going to need to be able to do is to be able to scale that direction vector to make it as long as I want. Remember that scalar multiplication doesn't change the direction of a vector. Well, I can just make the direction opposite. I guess it can change it, but it can't really change it, right? So I can make that green arrow like as long as I need it to, or if I need it to go the opposite way, I can make it do that just via scalar multiplication, right? Okay, so the point vector, we're going to use the symbol R0 to describe it. The direction vector, we're going to use the symbol V to describe it. And we're going to call our vector equation of the line R is equal to R0 plus VT, where T is just a scalar, it's a real number. So since T can scale vector R to be as big or small as you need it to be, you can then create every point that point vector that lies on that line with this equation. So this is my vector equation for a line. Everybody's cool with the symbols there and what things are representing? Again, the little derivation explanation I gave as to like what these symbols are and what we're really doing, not something that's needs to be repeatable. It just helps with like intuition, understanding like what exactly these symbols are and what it is that we're doing. God bless you. You're welcome. So let's look at a couple of examples then. So let's say we want to write this as a vector line equation. So I know my vector line equation is in the form R is equal to R0 plus VT, where the R0 was our point vector and V is our direction vector. So all I really need is to get a point vector and direction vector that I can plug into my formula and I'm done, right? So if we go back to this picture we drew before, was there anything special about this point 2, 2? Other than it was on the line? No. So any point on the line will be good enough for us to create a point vector from. So what's the point that is on that line, y equals 3x plus 5? 0, 5. Everybody happy there? It's the y-intercept. Or you could pick a value for x and plug it in to generate the value for y, right? You do that too. But whatever. Either way is fine. Now to get the direction vector, what do we need? The slope. What's the slope for this guy? It's 3. We'll write it as 3 over 1. So that gives us what direction vector? 1, 3. So then we can say an equation for our vector line is the r is equal to 0, 5 plus 1, 3 times t. Is this the only version of this I could write? How many versions do I have? Infinitely many. Why? Line goes forever. How many choices do we have here as our point vector? Infinite, right? There's infinitely many points. How many choices do I have here as a direction vector? Infinite. I could write that as 1 over 3. I could also write it as negative 1 over negative 3. I could write it as 2 over 6. I could write it as negative 2 over negative, like, I don't mean over, I'm sorry. But you got you see what I mean. Like, it's still the same slope, right? If we call the slope 3, or if we call it 6 over 2, or 9 over 3, or whatever, it's still the same slope. But those are different vectors, right? So when we ask you to write the vector line equation, there is no unique answer. Cool? Okay. What if I wanted to ask you to write this answer in linear combination form? Remember, the linear combination form is the ij one. So I'm just going to take the vector 0, 5 and write as 0i plus 5j, and the vector 1, 3 as 1i plus 3j. And then I still have the times t. Everybody cool with what I did there? Just change the form. And then what I would want to do is I want to do the scalar multiplication. So I'm going to distribute the t through, collect the I parts together and factor out the I, and then collect the t parts together to factor out the t. So put the I and j parts together. So there's that. Feel okay there? So another thing we should be able to check is if a point is on a specific vector line equation. So what we're going to do, this vector r is just represent some xy, right? Specifically, we want to know if it could represent this xy. Everybody's so far so good. What I'm going to do is I'm just going to do the vector operations here on the right hand side. So I'm going to do the scalar multiplication, then add the two vectors. So if I look at the x component, t has to equal 2. If I look at the y component, I'd get t has to equal 8/3. But do you see that? Notice that these are different t's. So what does that tell me then? That 0.213 does not lie on our vector line equation. If they were the same t, then it does. Basically all we're doing is seeing if there's a t that can generate that point, right? If I solve each coordinate for the t that I need to do it, they best be the same t if that point can be generated, right? Okay. What if we wanted to go the reverse direction? What if we wanted to write the vector line equation as a slope-intercept equation? Well, hopefully we remember from our algebra class that to write a slope-intercept equation, we need 2 pieces of information. What 2 pieces of information will do? A slope and a y-intercept, or a slope at any point will work, or 2 points, right? Those are the 3 possibilities that you could have. So from a vector line equation, the 2 easiest to get is either a slope and a point or 2 points. Getting the y-intercept is not that easy. So I'm going to focus on those 2 situations. To get 2 points, all I need to do is pick 2 different values at t, plug them in and see what I get. And those will be my 2 new points. Or if I wanted to do a slope and a point, that's what I would do. My point vector can give me a point. My direction vector can give me a slope. And now it's just an Algebra 1 problem. So y equals mx plus b. I solve for b by subtracting 9/2 from both sides, and then plug it all back in to get my slope-intercept equation. Mr. Kulik, sweet. I like it when a pre-calculus problem is just really like an Algebra 1 problem. That's pretty rad, right? Where was the pre-calc part? Was just this. Knowing that from the vector line equation I can do that, and we're good. We happy here? Worth pointing out, in 3 dimensions, is it going to be this easy? Definitely not, because in 3 dimensions, what doesn't exist? Slope. Yep. So that's a little bit of a slippery wicket there. All right. Last example here for today. So what if we want to find the intersection between two of these vector line equations? Now I'm going to stipulate that I agree that the easiest way to do this particular problem would be to just convert these into slope-intercept form and then solve it like the Algebra 2 way. I don't want you to do that now because the process that I'm going to show you will work the same whether it's in 2 dimensions or 3 dimensions or 4 dimensions or n dimensions, and will also become like a subroutine doing other things in the future. So I want us to practice this routine now when things are like small and simple and manageable, even though I acknowledge there's probably a faster way to do this particular problem in 2 dimensions. But as soon as you move it to 3 dimensions, it's not nearly as straightforward or simple to try to do it, translate it back to Algebra 2 land and do it the Algebra 2 way. Okay? So I'm acknowledging, yes, there's an easier way to do this, but I want us to practice doing it this way because in an extra dimension or many extra dimensions, this way that I'm about to show you is much easier than the alternative. Okay? Everybody's cool? Okay. Again, I want to be straightforward with you that, like, yes, I'm asking you to do it the hard way, a harder way now because it becomes easier later. I know that seems weird. Okay. So what's going on here? So I know if 2 lines intersect someplace, they have a point in common, right? Everybody agree with that? So if these 2 vector line equations intersect, they're going to have some point vector in common. I'm going to call that point vector xy. So in R1, that xy has to be generated by some s. And in R2, that xy would have to be generated by some value of t. Everybody's okay with that? What I'm going to do now is I'm going to just take this side of my vector line equation and perform the vector operations. I'm going to do the scalar multiplication and then the vector addition to write that side as a single vector. So I'd have 2 plus 1s and then 4 plus 3s and then negative 1 plus 3t and 5 plus 5t. Does everybody feel okay with how I did that? Okay. So if I look at the first equation, I see that x is going to be formed by doing 2 plus 1s. And if I look at the second equation, the same x could also be formed by doing negative 1 plus 3t. So I can say then 2 plus 1s has to equal negative 1 plus 3t. Since they both have to generate the same x, excuse me. Ugh. And I can say the same thing about the y's then as well. Everybody still feels okay there? Okay. And because the value of s that generates our x, I need the same value of s to generate the y. And likewise, we'd say the same thing is true about the t. That these 2 equations have to be happening simultaneously, which means that really what we have here is a system of 2 equations. So I'm going to go ahead and solve this system now. My first step in solving this system is going to be to rearrange it so I'm in kind of that standard linear form. So I'm going to subtract 3t from equation 1 and then subtract 2. So I'm going to move the variables on one side and the constants onto the other. We'll do the same thing in the second equation. And now what we'll do is we'll solve this system. If you remember back to your Algebra 2 class, we talked about a lot of different ways to solve a system. What was the fastest, easiest method that we had available to us there? Faster than elimination. Faster than substitution. I'm going to use a matrix and use the row reduced echelon form on my calculator because I don't have to do anything by hand. The calculator solved the system for me all on its own. I love that, particularly if this became like a 4 or 5 dimensional problem, because solving a big system by hand is a pain in the butt. Not that it's hard, it's just long and potentially quite tedious. So just as a refresher, the way to use a matrix on our calculator to do this, what I'm going to do is I'm going to open the matrix menu. So I'm going to press second and the -1 button. To enter a matrix into my calculator, I'm going to move over to the Edit tab. And I'm going to select a matrix to use. I'm going to use matrix D for our class. So once I select matrix D, the first thing I need to do is set the dimension of the matrix. If I look at my system, I have 1, 2 equations. So I have 1, 2 rows. So I need to make this 2 rows. And I have a column for my S's, a column for my T's, and a column for my constant. So that's 3 columns. And now the entries in my matrix are just going to be the coefficients from my system. So 1, and then -3, and then -3 again. And then we'll have +3. We'll have -5. And we'll have +1. So that's the formation of my matrix that I'm going to use. Everybody cool with how I created that? Again, the matrix basically looks identical to our system, just there's no variables or operations in there, right? It's just the coefficients. Okay. Once I've got my matrix set, I'll exit out of here by pressing second and then the mode button. I'll go back to my matrix menu, but this time I'm going to go to the Math tab. And I'm going to scroll all the way down to the bottom till I see the command RREF. RREF stands for row reduced echelon form. Basically what the calculator is doing is it's doing the Gauss-Jordan elimination algorithm on your matrix, which is basically just the elimination that you learned how to do on a system. It's just being applied to a matrix. But it's basically the same thing as the elimination that you guys learned. So I'll select that, and then I'll go back to the matrix menu again, and from the Names tab, I'm going to select that matrix D that we just made together, and then press Enter. Notice here that I got decimals. In this case, since the decimals are terminating, it's not that big of a deal. But if these were like non-terminating decimals, you might prefer a fraction. If you wanted to get a fraction out of this, if you press Math and then use the fraction command, it'll change your matrix entries into fractions. So let's write down just a little bit of notation about what we did. So we did RREF on the matrix 1, -3, -3, 3, -5, 1. And that gave back for me the matrix 1, 0, 9/2, and then 0, 1, 5/2. And somehow Mr. Kulik is telling me that that second matrix there is telling me the solutions to this system. So the way to read that second matrix is each row is basically an equation. So remember when we set up our matrix, the first column was the S's, the second column was the T's, and the third column was the solution. So if I read that first column in the same way, I have 1S plus 0T is equal to 9/2, or just that S is 9/2. Similarly, if I read the second row, that would be 0S plus 1T is equal to 5/2. So just T is 5/2. Everybody's so far so good? Now, does that mean that the solution or the intersection of these two lines is the point 9/2, 5/2? No. It does not. S and T are not coordinates for points. S and T were parameters that I used to generate points with my vector line equations. What's special about this S and T, it's that this S and this T, when I plug them into the appropriate vector line equation, will give me the same point, i.e. the intersection. So all I need to do is just pick one of these. So maybe I pick S. And then I'm going to just plug that into the vector line equation that had the S in it. And then just evaluate. So remember here, we have a vector, but 9/2 is a scalar, right? 9/2 is a fraction, not a vector. So when we do this, we get 2 plus 9/2, which is 4/2 plus 13/2. And then we have 27/2 plus 8/2, so that's 35/2. So that becomes the point 13/2, 35/2. And if I had chosen T and plugged it into the other equation, I would get the same point. And if you wanted to, you could check that. I'm quite confident that I did that correctly, so I'm not going to check it. But if you were so inclined to really make sure you understood what was going on, that's what you're getting there. So again, this is decidedly doing more than if we just converted these two equations into slope-intercept form and solved the system algebra 2 with algebra 2 methods. The advantage of this is if this was 3-dimensional or 4-dimensional or 5-dimensional, it's not really any more work because having bigger dimension isn't going to make any of these transformations that we did any more difficult, particularly since the calculator is handling the system piece. However, if I tried to translate a 5-dimensional equation of a line into like an algebraic representation, that's now non-trivial. That's not something I can just look at and write really quick. That's actually quite a bit of work. And we were able to avoid that using this method. Is that, you guys feel okay in terms of why I'm justified asking you to do it this way? We're going to do this with 3 dimensions in this course. So this is the other reason for me wanting to do it this way, is because it's clearer in 2 dimensions what's going on than it is in 3 dimensions, but it's the same process. This feels like a good place to stop. I'm going to stop here. At this point, you guys could now do problems 51 to 76. Note, though, that that's not going on to this week's problem set. I put that onto the next problem set. So for Sunday, we're really just going up to 50. And next week, we'll worry about 51 to 76 and some more. I think last time I had warned you that homework quiz was imminent. If it didn't happen today, do you suppose the probability went up or down that next class will have one? Up. And at this point, what sections would be fair for me to ask about? 1 through 3, right? Up until what we've done today. So if you were planning or preparing for a homework quiz next time, you'd want to make sure that you're up through 50 really in the problem set, or at least like, even if you didn't finish them all, I'm comfortable doing these problems because I've done like some out of all the sections and I feel like, okay, I got the idea. Like it's.
Well, isn't it 1 through 52?
Yes.
Yeah. So, okay.
So it should be, not everybody finishes stuff on time, right? Like that happens. I get it. Like we're just talking about like if you were wanting to prepare, what would you want to focus your preparation on? That's all we're saying, right?
There's no worksheets, right, for this chapter?
There is a worksheet, but we won't get to it until we're well into the last couple of sections.
Okay. And was this one of the hardest chapters you said for this semester?
I believe so. It's either this or the parametric polar that I think are the 2 most difficult. The good news is I think the next section is one of the easier ones, or the next chapter is one of the easier ones.
Did you ever curve test last year? I don't remember.
I don't think so. I almost never have to. The averages tend to be quite reasonable for the honors course. I mean, usually mid-80s or better. I mean, the last test, I think the median score was probably in the 90s. Yeah. So, like, why would I curve that? I'd have to curve it down.
We all just like curve this one.
Oh, I mean, usually the other impotence is that, like, we have the retake opportunity in the test double. So, like, if we have the test now. Yeah, like, if you really goof it, usually, like, you can make that up at the end. So, like, I tend not to worry too much about it. If it was like a real mess, that'd be something else. But usually this, even this, most students are able to do pretty well. The thing with this topic is none of the individual pieces that we're asking you to do are really difficult or that time consuming. Like the individual things are not hard to do. It's just keeping everything straight. Yeah, it's mostly like the name and the vocab stuff that like you understand what you can do with what and how to change things around to get something that's convenient to deal with.
And I mean the bearings take a bit, but I imagine there won't be a lot of those.
At most one. Look at the homework set. Did you even see a bearing problem in the homework?
I
I don't think so either.
Okay.
Sure.
Okay, so that's